Hello everyone. Welcome once again to this series of update webinars on the Oasys LS-DYNA environment software. As you'll know if you've dialed into the previous ones, these webinars have detailed the recent LS-DYNA updates and the latest features in the Oasys 17 software, which is available to download from our website. We'd usually provide this information at the user meetings we hold in various regions, but due to the current circumstances, this isn't possible. These webinars have enabled us to get the latest updates to you to ensure you know the exciting new features that are available in the most recent versions of the software. The webinar series kicked off on the 6th of May with an update on the LS-DYNA software. Our project manager, Jamie Talbot, also gave us a general update about how we're supporting those of you working from home, the acquisition of LST, and our software team here at Arup. If you didn't manage to catch the webinar, the videos are available on our website, and I'd recommend you watch if you can. So this is the final webinar in this update series. If you didn't catch the previous Oasys talks, you may notice a difference with our Oasys themed talks. The suite of products is becoming more integrated, with many of the new features and enhancements benefiting the whole LS-DYNA workflow. For this reason, we've moved away from the pre- and post-processing themed demonstrations to how the new features and enhancements aid that whole LS-DYNA workflow. Throughout the Oasys update webinars, I'm sure you'll have noticed the new user interface, which launched with Oasys Suite 17. This is a big change to the software, making it look more modern and accessible, and we're pleased that it's been so well received by those that have used it. If you want to find out a bit more about what's changed and why, you can check out the short introductory video, slides, and a frequently asked questions document on our website. So my colleague Alistair Parks and I are going to kick off this final Oasys update webinar, latest expert tools for LS-DYNA models. Right, let's kick off by talking about Primer keyword support. So in Primer 17, everything up to and including R11 is fully supported. So all keywords that exist in the R11 keyword manuals is supported. LS-DYNA R12 is mostly supported, though R12 is not officially released at the time of writing. So we've added in quite a lot of support for keywords in R12, but not all keywords are in there as yet. And this is, of course, added across volumes 1, 2, and 3 of the LS-DYNA keyword manual. So support for I10 keyword format. So some LS-DYNA small keyword format cards limit the field width to 8 columns. So here we have an example star node. It's got an I8 field for the node ID, and that limits the label range from 1 to 100 million. So since R9, LS-DYNA has offered an alternative I10 format, which is the same as the traditional small format, except any data fields less than 10 wide are promoted to become 10 characters wide. So Primer now supports I10 format in input and output, meaning 2 new soft label limit ranges. So I10, when you're running in single precision DYNA, limits labels from 1 to just over 2 billion. And then I10 64, so that's double precision LS-DYNA, limits labels from 1 to essentially 10 billion. Note that long format, where all fields are 20 columns wide, is also still supported. So now just a note about model read warning messages. So LS-DYNA doesn't accept include file paths if the length of the text present in a single line of keyword input is more than the specified limit. So that's 80 characters for small format and 160 characters for large format. And the problem can be solved by writing the model out from Primer, which will split the include path over multiple lines. So you can read these models into Primer and then write them out, and Primer will automatically fix that problem. However, you may just be reading your model into Primer to check it, and you don't write it out again. You don't necessarily spot that problem. So Primer will now issue a warning message if the keyword file contains include file paths of length greater than the LS-DYNA specified value. Now also when you read your model into Primer, you'll often notice errors and warning messages being printed into the text output area at the bottom left-hand corner of Primer. Now these can scroll by quite quickly when you're reading a model in and often can be missed. So now these error and warning messages are now saved into a separate log, and there's a new red button to the top of this dialog window that counts the numbers of errors and warnings since the log was last inspected. And you can see here in this example on the screen, we've got a number 3 and a little red button there. So you can then hover your mouse over that button and it'll give you some more details on those messages that are in there. And if you click on that button, you'll get a separate window that opens up where you can scan through those new error and warning messages that are printed in there. Okay, so moving on to talk about user-defined materials. So materials 41 to 50 in the LS-DYNA keyword manual are reserved for user-defined materials, and these are cards that can be used by external material subroutines. So any number of material parameters can be defined on the card because they're being fed into an external routine. And then these are used by the external material subroutines. So these parameters can be anything. So for example, they can be real numbers, they can be moduli, stresses, or they could be integers that are references to define curves in the model. So as the material subroutines are external, Primer doesn't know what the various material parameters mean. And this can lead to a variety of issues. So when renumbering, the link can be lost between a defined curve and a reference to the curve within the parameters. So let's say we've set a parameter to be 5 and that links to defined curve 5. Because there's no cross-reference there, if you renumber the model and 5 becomes 10, the material card will still reference the number 5. Defined curve definitions can't be viewed and edited directly from the material card. And the material card cannot be easily edited, and the correct field names applicable to the external subroutine are not displayed. So you can see in the example here on my screen, we have P1, P2, P3. So we don't see the correct field headers for the external subroutine in question. And any specified Young's modulus or Poisson's ratio values are not taken into account in Primer's advanced functionalities. So things like checking, changing unit system, and time step calculations, and so on. So what we've done in Oasys 17, and this is in Primer, you can now specify the field titles and the type of field for the user-defined material for materials 41 to 50 using a CSV data file that lives externally to Primer. And it looks something like this on the right-hand side here. So you can see the field names, as mentioned in DYNA in the first column. The second column is the name that you want to give it according to the subroutine. And in the third column is the type of data that's in there, whether it's a float, an integer, maybe a load curve or a table. The fourth column is a particular one if you want to specify which fields are Young's modulus and Poisson's ratio. These CSV files are then read into Primer using preferences. So because there are 9 material cards, so 41 to 50, you can specify a different CSV file for each of those materials because you might be using a different material subroutine for each of those materials. So down the bottom here, you can see some examples. So Primer star map 48 user defined, that points towards a particular CSV file, and then 45 can point towards a particular CSV file, and so on. So what's the benefit of having this CSV file? So this is what it looks like when you have a CSV file specified in Primer. So that's what we see on the left-hand side here. On the right-hand side is what you see when you don't have that CSV file specified. So as you can see on the right-hand side, we just have the generic names for the field headers. So U1, U2, U3, and all the numbers are displayed as floating point numbers. On the left-hand side, you can see the benefits of having the CSV file specified. So first of all, you can see the field names are displaying as they should be displayed for this particular material subroutine. And in particular, if you look at the second field in on the third row, so it's called LCK1, we've got 1209, the number in there. That is now a reference to a load curve. So you can see there's a drop-down arrow there. You can right-click, you can edit that load curve, and if that load curve is renumbered, the number will be updated on this material card in an appropriate way. So hopefully you can see that if you're working with these user-defined materials in DYNA, that specifying these CSV files, which could live in a central location and be accessed by everyone in your team, has huge benefits for being able to modify and edit these keywords. Okay, now to talk about measure and the explode tool. So one thing we've added to the measure panel is the projected distance on global coordinate planes. So if, for example, here you're measuring between node 1 and node 2, if we project that vector onto the 3 global coordinate planes, at the bottom of the measure panel, we report the length of that vector projected onto those planes. Another new measure option that we've added is the measure node to plane option. So you select 3 nodes to define a plane, and then the 4th node is the node that you want to know the distance between that node and the plane. So that's then reported both on the screen and in the measure panel as well. So in Primer, we also have the explode tool that explodes your model so you can view it in a different way. And that means you can view the contents in a slightly different way and understand what's in your model in greater detail. So in previous versions, we supported 3 different factors. There was a scale factor, a thickness factor, and a size factor. And all 3 could control the size of the exploded views. So these factors have now been rationalized into a single, all-encompassing spacing factor with a default value of 1. So this can range between 0 and 10, and a larger value results in a more separated view. Another thing we've added into Explode is the ability to drag. And this allows you to drag the exploded parts along the explosion direction. I'll just show you a demo of this in Primer. So here we have a model. We're just going to go up to the Explode menu. And the explosion center, I'm going to set to selection center. So that's just the center of the explosion is the center of the parts that I select. I'm going to set the spacing factor to 0.1. This is the new factor that replaces the 3 factors that were there before. And we'll just select a few parts. So I'll select the bonnet, the fenders, the deck lid. I click apply. And I'll just zoom out and you can see that they have been exploded. Now the new option here for drag, I can now turn that on. I can click on these items and drag them along the explosion path. So if you're wanting to create an image of your exploded model, you can use drag to fine-tune it and move things to where you want them to be. So I'll just talk a little bit about the interpolation option in the Orient panel. As before, the Interpolate button for Translate, Rotate and Scale is only active after something has been selected for orientation. But now when you select the Interpolation option, the tool pops up as a separate floating window rather than a docked window. And the default mode is the original search distance mode. And there's no major change to this mode. However, the sliders for search distance and order are now more in sync with their respective text boxes. Note as well, there is a new contour plot option for the search distance mode. And this plots the interpolation distance of every node within the search distance for the selected orientation option. If you're unfamiliar with the Orient Interpolation mode, the way it works is you specify the entities that you want to move. So in this example here, we have a a light blue part, and we've specified that we want to translate some nodes on that light blue part, and that's represented by the orange blob in the middle of the light blue part. Now we might want to move the nodes surrounding that selection as well and interpolate the distance that those nodes are moved. So that's what happens in this panel. So you specify a distance away from the orange nodes, and that's represented by this red circle. So every node within the red circle on the blue part will be moved. Now the orange nodes will move by the distance that you specify that you want them to move by. And then everything within that red circle, as I said, will be moved. But the distance that it does move will be interpolated from the distance away it is from the orange blob. So in Oasys 17, we've added a new interpolation option called Select Items. Now this is different to the search distance in that instead of the interpolation being based on a distance away from the selected area for orientation, it's instead based on what you select to interpolate. So let's take this example here again. We've got the blue part. And let's say we've selected the orange nodes for orientation. In this case, the red boundary of the blue part is fixed and does not move. And every node within the blue part, because it's been selected, will be moved. And that interpolation is based on the relative distance between the oriented items, in this case the orange items, and the fixed boundary. Let's just show an example here. Let's pick these 2 points on the blue mesh. And let's say these 2 points are halfway between the orange selected area and the red boundary, as you can see here. So these 2 points will be interpolated and moved by the same amount because they are the same relative distance between the orange items that you've selected to translate or rotate and the fixed boundary. So in this mode, you have options for adding the items that you want to interpolate. So in the previous slide, that would be the blue part. You can also remove nodes, elements, parts from that selection. And you can also specify what the fixed nodes are, so that boundary. Now, when you make your interpolated item selection, Primer will automatically work out the outer boundary of that selection, and they will be marked as fixed. But then you can change that as you see fit. Note here we have the option to automatically find the fixed nodes on free edges in your selection of interpolated items. So this is on by default, but you can turn it off if you wish. So let's just show you a quick demo of this. Okay, so here we have an example. We have a door inner panel. Let's just move it around. Let's say this central hole in the door panel. Let's say we wanted to move that inboard or outboard, but we wanted to retain the outer boundary of this whole panel. So essentially, we want to morph this panel. So you can do that using the new interpolation tool. So if I go to Orient, I'm going to translate those nodes along the inner boundary of this hole. So if I select Node and then Viz, Hole, and click on one node on the edge, that's going to select all the nodes around that hole. So those are the nodes I want to translate. Okay. Now I'm going to turn on the Interpolate option. I'm going to switch to Selected Items mode. I'm going to add the items that I want to interpolate, and that's going to be this whole panel. So if I click Add and select the part, Apply. Now, as you can see, all these blue marked nodes are the ones that are going to be interpolated, and the outer boundary, the free edge on the outer boundary, has automatically been selected as a fixed node boundary. That's because I've got this option on at the bottom of this panel. So I'll just close the interpolation panel, but that's still on, as you can see, in the docked panel. So I'm going to drag these nodes to move in the Y direction. Let's just drag them. And hopefully you can see I moved the nodes in the hole in the center of this panel, and then the surrounding nodes between the hole and the fixed boundary have also been moved, but it's an interpolated move based on the relative distance between the hole and the fixed boundary. So it's morphing this panel. So moving on now, just a couple of small but useful improvements to the remesh functionality. So we've added the ability to remesh multiple parts in one operation. Previously, when using Remesh Area, you could just select to remesh elements on one individual part. Also, the visibility of the elements is maintained after remesh, which didn't happen before. Also, if you're remeshing components which are made up of multiple DYNA parts, as you can see in this picture here, the internal part boundaries are preserved after remesh. So you can see here we're going from a coarser mesh to a finer mesh, but Primer has retained those internal boundaries between the different parts, which we didn't do before. Okay, so let's move on to Occupant Tools. And first of all, mechanism style connections for dummy assemblies. So prior to Primer 17, it was not possible to create a dummy assembly tree where one assembly had multiple parents. But these more realistic systems can be found in newer dummy models. Okay, so what do I mean by that? Let's take this very simple diagram of a dummy model. We have the parent assembly, and that tends to be the pelvis. Now that parent assembly has children. So here we're showing the thorax and the upper legs. And those assemblies have their own children. So we've got the upper arms, the head, the lower legs, and so on. And so on we go down the tree. So we have this parent-child relationship, but it was not possible before to have an assembly which had multiple parents. But here, if we have a look at the Humanetics Thor model, here we have the clavicle assembly and the shoulder joint. Now this is an enclosed mechanism which is attached to the thorax in two locations. So in this case, you have a child and you want it to attach to a parent in two different locations. So here you can see we've got a self-contained clavicle mechanism, and it wasn't possible in Primer before to set this up using the tools that we have. So introduced in Primer 17, a child dummy assembly can now have multiple parent assemblies. One parent with a regular XYZ rotational connection, and others with a pin line hinge connection. And essentially, this is an enclosed mechanism within the dummy assembly structure. So the new options, pin, line, and hinge, are designed to permit assemblies to be children of multiple parents. And they can be found on the assembly edit panel when specifying children of an assembly. So this is quite a niche tool, so it's probably of interest to dummy manufacturers, but other people might want to modify their dummy trees as well. So please have a look, and if you want any more information, please let us know. Okay, so moving on to dummy tilt sensor measurements. So I'm going to go straight into a demo for this. So here we have a primer session with the Thor model read in again. So in reality, the real life dummy has instrumentation that measures the relative angle of various components within the model compared to the global coordinate system. So these are tilt sensors. So the dummy model here contains beams that are used to measure the relative position within your model as well. So it's useful to be able to use those instrumentation beams to compare against any test measurements that you might have. And that means you can position your occupant to match the test position more accurately. So we've now added a tool into Primer that allows you to see these angle measurements more easily. So if I go to Safety and go to Dummies, there's a new Measure button down here. So if I click on that, so here you have a list of beams, measurement beams in the model. Now there's a text filter here which says tilt beam and has some wildcards in there. And that's pre-populated, but you can change that to whatever you want. But at the minute, that's found all the beams that I want in the model. So if I select them all, click Apply, you get this panel. So here you can see I've got all my tilt sensor beams, and it's reporting the measurement angle between the beam and the different global coordinate planes. So here we've got the XY plane, YZ plane, and ZX plane. So here you can look at the measurements, compare them against test, and you can move your occupant around till you match the test measurements. Okay, so I'd like to talk a little bit now about simulation-based dummy positioning. Okay, so just as a reminder, simulation-based dummy positioning, this is where you use Primer to set up an analysis that you run in LS-DYNA that will position the occupant. So here we're seeing some examples of an occupant being pulled into position, both the arms and legs and head being moved into position, but also being moved into a seat. So this is beneficial because then you can use all the contacts that exist within the complex dummy model and the seat, so that you don't end up with initial penetrations that you might end up with when you're moving the occupant around within Primer. So in Oasys 17, we've made a few additions to this. So previously, you had to specify 3 nodes per assembly to attach cables to, and those cables are used to pull the occupant into position, as you saw on the previous slides. Now we have options of 1 node, 2 node, or 3. So the 1 node option allows you to specify 1 node per assembly to create the cable to attach to, or for 2 nodes allows you just to create 2 nodes, and so on. The 3 option gives you freedom to put 1, 2, 3, or 0 nodes per assembly for the cables, so you don't have to specify them for certain assemblies if you don't want to. Now if you click on automatically determine nodes in this panel, while the 3 option is selected, then Primer will calculate 3 nodes per assembly as it did before. Note as well that we have also added command line support for all of the above as well. So if you're using this as part of an automatic process, you can do it that way as well. So you can see what this panel looks like in the various different configurations. So on the left-hand side, we have 1 node specified per assembly, and the next one along, 2 nodes per assembly. The next one along, as it worked in version 16 and before, we have 3 nodes per assembly. And on the right-hand side, we've got the 3 option where you can specify different number of nodes for each assembly, maximum of 3 and the minimum of 0. You don't have to specify them at all for a particular assembly. And that might be useful for a very small assembly that's maybe used for positioning and so on. You don't want to connect a positioning cable to that. Okay, so I just want to talk a little bit about human body models. So human body models are biofidelic FE models frequently used in several industries and often used in pedestrian and occupant impact and protection. They're a very useful way of understanding how a human body will react in a crash event. So the 2 industry-leading human body models include the Global Human Body Model Consortium, that's a GHBMC model, and the Total Human Model for Safety, THUMS. However, these human body models are received without the ability to be positioned in Primer. Positioning is now possible, though, with the addition of a Primer dummy tree. So for Primer 16, we introduced Primer dummy trees for various THUMS models. For Primer 17, we have improved these trees and also created trees for the GHBMC 50th percentile occupant model. So a dummy tree is a star end keyword, which means it's written after star end. So LS-DYNA will not read it, but Primer can read it, and it defines beams, joint stiffnesses, parts, and assemblies. And when read, this results in the ability to articulate joints and position the human body model in Primer. So dummy trees are separate include files, and they're available upon request. And the trees are specific to a particular human body model and are in the form of an include file, as I said, and it's called data-for-primer.key. And you can use a text editor to include these in your models. So Primer property files have also been created that change the appearance of the human body model, making it easier and simpler to use the positioning tools. So in Primer 17, the dummy and seed squash tool can be used to specify target positions. And the flow diagram here outlines the process of positioning. So you launch the tool, and then you can specify either a single position or multi-stage position. And then you move the occupant into the position that you want. And once the human body model is in the desired position, Primer will automatically calculate the displacement cables required to pull the model into position in LS-DYNA. Now, during the analysis, multiple DynaIn files can be produced by LS-DYNA, and these contain the updated nodal coordinates of the final position. Once you have these, you can import these back into Primer, and you'll have your positioned occupant model. So here we have an example of a single stage positioning analysis for the GHBMC occupant model. So single stage means we're moving everything at once. We're moving the arms and legs into position in one stage. And here we have an example of a multi-stage positioning analysis. So here the occupant is moving up, the arms are moving into position as a second stage, and the legs are moving into position as a third stage. So occupant moving, arms moving, legs moving. And here we have another multi-stage positioning analysis. So first the legs move into position, hands move into position, head moves into position. And then we move the head, arms and legs in one stage to a separate position. And this might be appropriate in one analysis to produce two positions and write out two DynaIn files that can be used in your analysis. So in summary, we've developed dummy trees for a range of occupant and pedestrian thumbs and GHBMC human body models. So these include the following listed below. So these models are supplemented with an additional guide to positioning and a properties file, as I've mentioned. So please let us know if you'd like to try out these dummy trees in your analyses. Okay, so some changes we've made to the part compare table now. And I'm going to go straight into a demo for this. So here we have two models read into Primer, two vehicle models, as you can see, Model 1 and Model 2. And there are some small differences between these two models, and I want to use Primer to investigate those differences. So if I go to Part and then click on Compare, this is the panel where you can compare part information across models. So it doesn't just do this by comparing the part keyword cards, it also compares the part properties. And what I mean by part properties is that all the different fields that we display in the part table that contain information about the part. So for example, part mass, number of elements, material data, Primer will compare all that information and show you the differences. So if I click on Model 2 as my modified model, you can see it brings up the part table in a special mode which displays the comparisons. So the grey rows here contain part information for a part in Model 1, and the white rows contain part information for a part in Model 2. And we're just displaying the parts that show differences in the data between the models. Now, quite a few of the differences in this table are due to the include file name changing between the two models. So I'm just going to turn off the includes column and refresh this table. And I now have a smaller, more manageable number of parts to look at. So there's various differences in here. For example, these top few parts, you can see there's a change in material modulus, and that has led to a change in the smallest time step being calculated for those parts and the added mass being calculated for those parts. Further down, we have parts with a difference in mass, and you can see there's a difference in number of elements here. So these could be remesh parts or perhaps parts with different geometries. So this functionality existed in previous versions to Oasys 17. But in Oasys 17, we've had the ability to write this information out to an Excel file. So if you write it out through this panel, you get an Excel file that looks something like this. So here we have the information in the part table written out into an Excel file. As you can see on the left here, we have Model 1 information. On the right, Model 2 information. We have image snapshots of the parts for your reference. And then the differences are highlighted in red. So you can see here we have difference in the added mass and the modulus and so on. So this is a useful way of writing out part comparison information from Primer to an Excel file. Moving on to changes in the check options panel. So the check options panel has been redesigned. At the top, there's two new buttons for element quality checks. So reset will restore the options to the initial state when the panel opens. And then save element quality settings to OAPref. We'll write all your currently set settings to your home OAPref file, which means when you open Primer again in the future, you don't need to set them again. It will read the OAPref file and set them to the settings that you want. Note as well that the element quality check values can now be set for different element types. So for example, you can set different angle limits for shells, solids, and thick shells. So previously you had one setting that applied to all element types, but now you can set different settings for different element types. And finally, time step and added mass checks can now be accessed via the quality criteria as well. So in Primer, we have a tool for setting up seatbelt anchorage type load case analyses. And we've improved this in version 17. So first of all, the belt fitting stage has been improved to produce a better seatbelt fit. We've also added an option to set torso points to known positions, which can aid belt fitting. We've added an option to align the shoulder block automatically or manually. We've also added an option to update the 1D seatbelt element length when fitting the belt. We've also added a new option to install an inertia bar and apply the appropriate load to the seat as per the regulation. So I'll just show a demo of this. So here we have a model and we want to set up seatbelt anchorage analysis. So if I go to Safety and go to SBA Automation, we have the panel. And here you can specify all the various points that we want to attach belts to and so on. But you don't have to do that every time. You can save out your settings and read them back in at a later date. So I've got some settings that I've saved out. So if I read those in, see it's populated all the information required in this panel. If I click on the Apply Inertia button at the bottom, this takes me to this new panel where you can specify all the inputs required for the inertia loading device, which has been added in to Primer 17. So here's the load and so on. So I'm going to click on Calculate. This reads in the standard blocks that you get with Primer. And at the bottom, hopefully you can see the inertia bar is being positioned against the back of the seat towards the bottom. Now we're positioning the blocks into position here, and the upper block as well. And now we're going through the process of refitting the seat belt around the blocks after they've been moved into the correct position. So this just takes a few seconds to run through all the iterations, And there we go. So if I click OK and dismiss, you can see now we have the blocks being positioned into the seat. The seat belt has been refitted around those blocks, and we have the inertia bars positioned in the seat and applying the load at the bottom of the seat. So now I'd like to update you on the new features in our pedestrian tools. First, I'll update you on the HIC Area Calculator in Primer. This allows you to import some HIC results and then visualize those in your model, as well as do some sensitivity studies and calculations based on those results. So in Primer 17, it's now possible to show both name and value text fields at the same time, which you couldn't do before. You also have the ability to increase and decrease the screen text size, which depends on screen resolution. One of the main things we've changed is at the bottom of this panel, where we've reorganized the GUI into 4 separate tabs. So the first tab, the Calculation tab, is for inputs for regulations. The second tab, Points, contains tools for modifying HIC data points. The third tab is Analysis, which has advanced analysis tools. And the Utilities at the end has some other options as well. Another thing to note is the contour bar max-min values can now be more obviously changed than they could be before. So the new Calculation tab contains the regulation choice option and the corresponding calculation limits. So here in these images, the regulation is Euro NCAP, and you can see the limits being displayed there. And you can change those limits, obviously. But it's also now possible to modify these HIC limits by applying a scale factor. So let's say you apply a scale factor of 0.8, that will change all the limits by a factor of 0.8. So limits can then be reset by clicking on this reset button as well. And I'll show you this in an example in a minute. The new Points tab contains options for modifying HIC points. So a new option here is to be able to filter the displayed HIC points by adult or child or cyclist. And we've also added in new functionality to delete points, edit the HIC of multiple points at once, and also you can apply an offset or scale factor to HIC values. So these are all tools that allow you to modify the HIC values and see what effect that will have on the overall Euro NCAP points or the overall area calculation. The Analysis tab contains the advanced analysis tools. So this is where you'll find the previous GTR tools for area sensitivity and target percent area. There's also a couple of other options in here. One is the bidirectional band sensitivity option, and this is to separate the points that are risk at getting worse or risk at getting better. Previously, they were both displayed at the same time. We also have the target NCAP score, where you can type in what your target score is, and Primer will tell you which points need to change and by how much to achieve that score. And I'll show you a demo of this in a minute. So the Analysis tab has a new option for excluding points from these calculations. And this is applicable to area sensitivity and the target score calculation. So here you can identify the points to be ignored from these calculations. So this allows you to limit the focus of the calculations to specific areas of interest or to avoid areas that would not be feasible to change. So if we take the example that's shown here, this is area sensitivity. So here we're plotting the areas that Primer thinks are the most likely to give you the biggest bang for your buck if you were to change the HIC and you want to improve the area in the GTR calculation. But the areas that have been identified, so the highlighted areas, it may not be possible to reduce the HIC in those areas for whatever reason, for design reasons, for packaging reasons, whatever. So you can remove those from the calculations, and then that will leave the plot on the right here, which will then highlight the areas that you may have a chance of changing through design changes. And finally, the Utilities tab. So this contains other additional functionality. So it's got the previous options for combining data with a second input file, writing out a blob file and saving your settings. And there's new functionality in there as well. So there's two additional preference values that can be saved, which is the delta for band sensitivity and the delta for area sensitivity, and also the ability to restore data back to the original blob plot. So I'm now going to demo a couple of things that I've just talked about. So here we have a new session of Primer, and we're going to start the HIC Area Calculator by going to Safety, Pedestrian, HIC Area Calculator, which opens this panel. Now the first thing we want to do is read in some data. So we're going to click on Read Data File to read in a data file containing XYZ coordinates and HIC values. So that reads the data in and plots the points on the screen. Primer will automatically calculate the band around these points. And you can use the display options at the top to turn these on and off. And here is where we can turn on the text, so we can show the values, so those are the HIC values, or we can show the name or both now. So I'll just leave the name on for now. At the bottom are the 4 new tabs that I mentioned in the PowerPoint slides. The first one is calculation. So this is where you can change the regulation. So let's change from GTR to your NCAP. So that changes the calculation, and you can now see that for these points, we have a normalized score of 16.3. And here you can also change the bands for this particular regulation. So the new option here is a scale factor that I can type in a scale factor of 0.8. So that applies that scale factor to these band values. And you can now see that these points, according to the new band values, gives me a score of 13.5. So many people will work to a lower band values than the actual regulation to make sure they meet their targets. So let's now look at the Points tab. And if I go into Points, there's now options here where you can choose which points you want to display. So if I can choose the adult points and just show those, or the child points, or the cyclist points, I'll switch back to showing all. And in here, we also have the new option for offsetting or scaling points. Now just switch to the Analysis tab, and this is where you can do band sensitivity. But the new option here is for calculating a target score. So if I click on this, and as I said before, my current score is 13.5. Let's say I wanted to target 16 points. So type in 16, click OK. Now it's asking me, do I want to exclude any points from the calculation? So I'm going to say yes, and I'm going to select the top 2 rows shown on the screen here. Now this is for areas where you know you're not going to be able to change the HIC values in any significant way. Maybe the packaging is too tight, you can't make any design changes. So let's just say these top 2 rows. I know I'm not going to be able to reduce the HIC at all. I'll click Apply, and Primer has calculated the points that need to change to achieve the target specified. And at the bottom in the dialog box, you can see it says to achieve a score of 16 points, 67 impact points must change bands. And the largest change is 186 HIC. So all the ones highlighted are the ones that would need to change to achieve that target. So giving you an idea of where the design changes may need to be to help you achieve your target. So for example, the one I'm moving my cursor over at the minute is currently a yellow point, and for it to go green, it needs to be reduced by minus 126. And so if you make changes to achieve the targets that have been specified here, you should achieve a target score of 16. Now with band sensitivity, this again, you specify a HIC value. If I click OK, this is the new option here. Now previously, Primer would show you the points that are close to getting better or getting worse. But now you can choose whether you want to see both or better or worse. So if I click on better, so this is highlighting the points that are close to changing to a better score, a better band. And it's telling me that if I did change all of those points to change the band, then my Euro NCAP score would change from 13.5 to 14.25. Finally, the utilities option at the end has various utilities for combining input data, saving settings, and so on. So if you're using Primer for pedestrian impact, please do check out the new features in the HIC Area Calculator. And just to mention reporter templates as well. So we have reporter templates for automatically post-processing your pedestrian runs. So each time you run a pedestrian head impact simulation, you can automatically generate a report of the results using the new reporter templates for your NCAP and GTR assessment protocols. The templates interface with the HIC Area Calculator that I've just demonstrated to you to show band and area sensitivity results. So you can automatically generate the band and area sensitivity plots that you can see here using reporter templates.
In Oasys 17, you can now visualize the thickness of shells in D3plot. Now, just to be clear here, we're not talking about LS-DYNA's thick shells. We're talking about visualizing the thickness of regular thin shells, star element shell. In Primer, you may already be used to visualizing the thickness of shells. You can do this by going to Display, Options, and then switching between drawing shells with a thin line, true flat, or true smooth. And this will change the view for the whole model. So I can focus on just the front bumper, and then hopefully it will be clearer that when I switch between thin line and true smooth, then the thickness of the shells is visualized. In Oasys 17, you can now show the shell thickness in D3plot too, but it works a little bit different. So I'll give you a quick demo. In D3plot, we've added the extra control to show the thickness of shells on a part-by-part basis. And that's mainly because when the models get really big and you're visualizing contours, then showing the thickness of shells can start to slow things down. So to draw the thickness of shells for a single part, you can right-click on it and go to Shell Thickness, Draw Shells with Thickness, and the thickness is now visualized. To make this change for several parts at once, you can go to the Quick Pick menu and choose the Draw Shells with Thickness option, and then draw a selection box over the parts you wish to change. You can also control the selection from the part tree in a similar way. So here, I'll right-click on the whole model and then choose Draw Shells with Thickness. Now, if I plot some results, then hopefully you should be able to see that the results have been mapped onto the thick shells. But it's worth noting that the same result is drawn on both the top and bottom surfaces of the shell, so you're not seeing any through thickness variation. To see the results for different through thickness integration points, you would still need to change the integration point you're drawing from the normal menu. D3plot extracts the thickness data from the D3plot or PTF results file, and so the thickness values will be drawn correctly if they change thickness over time. If those thickness data aren't available in the results file, then D3plot will take the part thickness from the ZTF file and draw that instead. Now I'd like to tell you about curve locking and freezing, which are new features in THIS. You might already be familiar with the concept of locking in Primer and D3plot. So if I select only the include file containing these front doors, then I can press the lock button down here. And then when I blank further parts, then if I press U on my keyboard to unblank, then it will only unblank to my locked blanking state rather than unblanking the whole model. If I toggle the lock button again and then press U, it will unblank the whole model. So in version 17, we've added a similar feature to THIS. So if I blank a curve, I can then hit the lock button on each graph. And then when I blank further curves, if I press U to unblank, then it will return me to the locked blanking state. And if I toggle the lock button, then I can press U to unblank all of the curves again. This is particularly useful in a session with a large number of curves when you want to only leave a select few curves unlocked in each graph, preventing accidentally unblanking all curves. And as well as locking, there is another new feature in THIS called freezing. So if I right-click on a curve, I can freeze the curve. And this is the equivalent of locking, but for visible curves. Freezing a curve on a graph will stop it being blanked until it's unfrozen. So if I try to blank all these curves, then the frozen curve will remain visible. I can unfreeze a curve by right-clicking, unfreeze, and then it's possible to blank it as normal. It's also possible to control locking and freezing in the curve table. If I press the locking freezing mode, then I can lock curves that are already blanked. These will show up as red, or freeze curves that are already visible. They will show up in green. We've made some datum enhancements for THIS 17. Constant datums can now have a second value with a corresponding second label, and a third fill color can be used to fill in between the two values. So in this example, we've selected the color yellow to go between green and red. And you can now orient the datum labels vertically as well as horizontally. If I go to the datum menu in THIS, then I can show you that for points datums, it's possible to copy points from a curve with this button here. You can either select a curve from the list or select it directly from the graph. I'll choose a color to fill below my datum, and using the new custom color feature, I'll pick one of the colors I've saved earlier. I'll give this datum an acronym, and then hit create. So now you should find it much quicker to create datum limits from curves. And another quick trick, if you want to only fill the area between two curves with color, then you can create another datum. So I'll select points again, copy points from curve, and pick the other curve. And this time I'll fill below with the background color of the graph. And with these features, it's possible to do quite a lot of different interesting visualizations in THIS. I'd like to end this webinar by talking about something really exciting: equations. In version 17, we've added a new equations feature to help you quickly manipulate your curve data. In THIS, there is a new equation option in the read panel, which allows you to input an equation of the form y equals f of x and plot the corresponding curve. Here you can write any of x, t, or time in place of x. You can also reference curves in these equations using the curve number preceded by either the letter C or the hash symbol. For example, y equals curve 1 plus curve 2 is valid, and this allows multiple individual curve operations to be replaced by a single equation. So in THIS, if I go to the read menu and select the new equation option, then I can enter an equation. So here I'm going to enter sine of 2 times pi times x. And then you can either enter your own range of x values for the curve, or you can take x values from an existing curve. When I click apply, THIS creates the curve. And it's possible to edit existing equation curves by right-clicking on them and selecting edit equation. Here I'm going to increase the frequency of my sine wave. And when I click apply, then the original curve is updated. And remember, we can reference different curves in our equations. So if I edit this black curve here, then I can modulate it with the sine wave I've created by multiplying by hash 2 that's curve 2, and then adding an offset. If I click apply, then you can see that the curve has been modulated. So when would this be useful? Well, in THIS, you could replace a whole load of operations with a single equation. And also in Primer, it's possible to define curves using equations. This is useful for easily creating and modifying curves without having to generate a list of points. You could use this when defining boundary prescribed motion or applied loads, when specifying gas properties on airbag cards, or for any of the curves involved in material properties. So in Primer, I have this test model with a define curve function. Now, define curve function allows you to specify a curve with an equation. Let's pretend that this curve is for a load curve. I can now visualize this curve in THIS. When I click the THIS button, the curve appears on my THIS graph. And if I blank the sine wave, then you can see that it's actually matching the modulated signal I created earlier. So now we're viewing the load curve from Primer. We might decide we want to edit the curve. So here I'll edit equation as before. And let's suppose I want my model to both load and unload now. I can make a quick edit to the equation, click apply. And if I'm happy with the result, I can then right click on the curve and click update curve in Primer. And now the equation has been updated in the define curve function keyword. All I need to do is click update to save the changes. And even if equations aren't that exciting, I hope that it's another useful tool to help you with your models.
Thanks, Alistair. So just before we wrap up, a quick reminder about the new features information available on the website. These PDFs provide more information on the new features in each of the individual programs in the Oasys Suite. They can be found in the Oasys Suite downloads area under documentation. I hope you found this webinar, along with the others in the update series, useful and interesting. If you have any questions on the material presented or anything related to the Oasys software, Alistair and I are online now and you can contact us through the question box. You can, of course, contact us at any time through your usual support channels. So this concludes the series of webinars to update you on the new features of LS-DYNA and Oasys Suite 17. Our usual webinar program does, of course, continue. These monthly webinars provide information on specific features or tools within LS-DYNA and the Oasys Suite. We have the next two planned for June and July, and we'll be uploading the webinars for the second half of the year soon, so please do check back. You can find the webinar page under training on our website. So thanks again for listening. If you have any questions now, as I said, Alistair and I will be happy to answer. Just contact us via the question box, or do get in touch at any time through your usual support channels. Bye for now.